Hello, hello. Sorry for not doing the fiddler last week. I had a really busy week, and I looked at it, and the first part, the main question, was kind of a well-known question, and I didn't really feel like I had anything to add anyway beyond what you could read in a Wikipedia article about derangements. So if you're in trouble with the first one, go look at the Wikipedia article on derangements. And then I briefly looked at the second one. It wasn't obvious to me how to do it, so I just didn't have the time to dedicate to it. So apologies for that. But this week we have one that's right in my wheelhouse. So here we go. The game is as follows. So I've got a player who is going to do the following. They're going to spin a huge wheel, which gives me a result, which we're going to call x1 from the uniform distribution between 0 and 1. And then they have a choice. If they want to, they can spin the wheel again, and they're going to get another result, which we're going to call x2 from that same uniform distribution. And now, if I spin once, I get a result, which is just my first spin, that x1 value. But if I spin again, I get the sum of those two values. Uh, the and then it goes, if that value I get, whether it's just the one spin or the two spins, is more than one, second player immediately wins. If it's not more than one, then they get to go, and they do the exact same thing, right? They're going to get a first spin from the uniform distribution, 0, 1, and if they want to, they can spin again, and they're going to get, so I'm going to call those y1 for the first spin, y2. I don't think I'm ever going to use those, but if I do, they'll be y1 and y2, and then capital Y will be the total that player 2 gets. So if the total that player 2 gets is between x and 1, then player 2 will win. Otherwise, player 1 will win. So that's the game. It's based on the Price is Right wheel, except instead of having just every nickel, it's a continuous distribution here. So what's the probability that player 1 wins? That's the eventual number we want to get to solve this problem. Okay. Well, the important things we need to figure out here is, when is a good player, from a game theory perspective, going to spin again, and when are they not going to spin again? And we're going to use backward induction. So this is a very common game theory technique, especially in sequential games, where you start at the end of the game, and there's really not much to think about going forward. And so you could figure out what the kind of last choice will be for the last player that moves. And then once you figure that out, you can use that for previous decisions, right? You can, if you think about what the state of the world is going to be like at the end, you can figure out what that player is going to do. Once you know what that player is going to do given its inputs, then you can figure out what to do with the previous step, and so on, back to the beginning of the game. Now here, there's only two choices, whether player 1 spins again and whether player 2 spins again, so the induction is not that far. But in theory, you could do this as many steps as you want. So when is player 2 going to spin again? Well, this is pretty simple. So if the number they get is less than the number they have to beat, they're going to spin again, because if they don't spin again, they're just for sure going to lose. So they really don't have a choice. They're going to spin again. So for a given x, if suppose that player 1 manages to not go over 1, and it gets to player 2, what's the probability that player 2 is going to win? Well, it's this. So the left part is the important part, and that will simplify to 1 minus x squared. I'm going to get into where that first part comes from, but just for now, if the probability that the player 2 wins is 1 minus x squared, that means the probability that the player 1 wins is just x squared. So the important takeaway here is, the thing we need to remember is that if player 1 ends the round with some total x, then the probability that they win is that total squared. So how do I get the first part? How do I get this 1 minus x times 1 minus x? So I'm going to break this down into two parts. First is, what is the probability that player 2 wins on the first spin? Well, that's the probability that their spin is bigger than x, which is just 1 minus x. Right, it's all the distance between x and 1 that is available on the uniform distribution. Now, what's the probability that player 2 wins on the second spin? Because those are the two possibilities. Right? If player 2 wins, it's either they did it on the first spin or they did it on the second spin. And those are mutually exclusive, because you can't have them both spin. You can't have them win on the first spin and the second spin. So if I add these together, that's going to be it. And those are the only two ways the player 2 can win. So they have to have not won on the first spin, so that happens with probability x. That's where the first x and x times 1 minus x comes from. And then the second spin has to get them in total above x but below 1. So what's the probability of that? Well, if you can backward induce this, I guess, from the final result we get. but that's just going to be 1 minus x. You might think it depends on what their first spin is, and I think that's a very intuitive thought, but unfortunately it's wrong, right? So if the first spin is less than x, it doesn't matter what that first spin is, you're going to end up with the same probability of winning on the second spin, and that's 1 minus x. So why is that? Let's think about this number line. And suppose I have some given x, that's the player one total coming into it. And on the first spin, the probability that I win is just this kind of red target area, right? This distance between x and 1 that I could possibly get to. And now, if I don't win in the first spin, my possible outcomes kind of shifts up a little bit. So I get some y1, some first spin value that shifts up the total things that I could get. But the range that I'm looking for, my target range for winning, is exactly the same as before. It's just on a different part of the line. So no matter what that first spin is, it really doesn't matter. I'm going to have the same probability of winning on that second spin, and so it's just 1 minus x no matter how you slice it. So player one, they now know that they win with probability x squared if they get it to player two. So when are they going to choose to spin again, right? And now we can do this backward induction because we got to this x squared knowing what player two is going to do, and now that we know that x squared, we can decide what player one should do. So again, that probability of winning, if I just take my first spin, is whatever that first spin was squared. Well, now I can calculate what's the probability of winning if I take another, and if that's more than x1 squared, I should spin again, and if it's not more than x1 squared, I should not. So I get this integral, right, where it's really not as complicated as it looks. The left side of this equation is just the integral from 0 to 1 minus x1. So again, x1 is the value of my first spin, whatever that is. And I'm integrating from 0 to 1 minus x1 because those are the possible ways that I don't go over 1, right? So if x2, my second spin, is between 0 and 1 minus x1, I'll end up less than 1, and I'll end up being able to keep playing. And then what's the probability of winning in that scenario? It's whatever that sum is, because my integral range already guarantees that my value will be less than 1, and so I don't have to worry about that edge case. And so the probability of winning is just that total squared. And I'm integrating that over the possible values of the second spin. And then I'm just taking that integral, right? So the integral of x1 plus x2 squared from d2's perspective is x1 plus x2 cubed over 3. I'm going to evaluate that at the top of the integral, subtract it from the bottom of the integral, and that's just 1 minus x1 cubed all over 3. So that's the probability of winning if I take another spin. And this is for any value of x1, right? Any value of x1. The probability is 1 minus x1 cubed over 3. Now the question is, when do I choose to spin or not? So this is just an explanation of why that integral only goes to 1 minus x1. And so I take this value, 1 minus x1 cubed over 3. If that's greater than x1 squared, then I'm going to spin again. And I just solved this numerically. There might be an algebraic way to do this, but it wasn't obvious to me. So I just numerically solved that, and I got 0.53209 about, and I'm going to call this value t from now on because that's the threshold value for whether player one will spin again. Okay, so now what's my probability of winning? Well, if x is less than my threshold, I'm going to use the probability of winning in 2 spins, and if x is greater than the threshold, I'm going to just use x squared, right? And that's it. So I get this double, it's not a double, it's 2 integrals that I'm adding together. First, I'm integrating from 0 to the threshold. Now, I should call this x1, but I'm just calling it x, of 1 minus x cubed all over 3 again. That is the probability of winning, assuming I spin again. And if my first spin is between 0 and the threshold, I will spin again. So that's the probability of winning, given that my first spin is between 0 and t. And then I go ahead and do the probability of winning, assuming the first spin is between t and 1, which is just that value squared. And you can do that integration, and it's about 0.45. So that is the answer to the basic question. I'm going to speed along through and try to just get the basic intuition behind the extra credit. There's a lot of algebra and a lot of things to be careful about. I'm not going to go too deep into the algebra or the calculus, I guess, but I will try to catch all of the kind of important sticking points here in this. So the extra credit is, what if we had a third player? So all the stuff we've done is going to be very helpful because basically using this backward induction method, player 3 in the new game is going to look like player 2 in the old game, almost exactly. In fact, exactly, they'll look like player 2. Player 2 will almost exactly look like player 1. We'll talk about a little bit of sticking point there. And then player 1, we're going to have to do a lot of work on. So third player, when are they going to spin again? Same deal. If whatever the value they're trying to beat is, if their first spin is less than that, they're going to spin again because otherwise they lose. So they're going to do that. So second player, right? The reason they're different is they have two things to worry about. Assuming player 1 didn't go over 1, they have a choice about when to spin again, and they have two things to keep in mind. First is, did they beat player 1? If not, they have to spin again, right? No question. If they did, they still are in the shoes of, well, player 3 is going after, so I still have this question of, do I want to spin again to increase my value, to increase the likelihood that I beat player 3's spin? And so they're going to have to do a similar threshold question. But fortunately, the threshold for them is exactly the same as the threshold from the previous game because everything is exactly like it was in that game. There's one player going after you. They have the exact same rule set. So assuming that your spin is higher than player 1's spin or they busted, then your threshold is going to be exactly the same. If you're not higher than player 1, then you've got to spin again anyway, so it doesn't matter. So we know their threshold. I'm going to start calling that T2 for the second player threshold. And now we need to figure out, well, what's the threshold for player 1? Because they're in a similar situation as the real player 1 in that they are going to spin once, and then they have a choice about whether to spin a second time. And they have to choose whether or not to spin again, and they're trading off these considerations about the other two players going ahead of them. So basically, we're going to have to figure out what's the probability that player 1 wins with some given score. Probably should be capital X there, and we might think that it's just x to the fourth, right? Because the probability of winning in the two-player game was x squared, and so basically, given that player 1 goes, right, they've got to beat player 2, which you might think is just x squared, and then they have to beat player 3, which should also be x squared, right? If the theory from the first game should hold, but that's not quite right? This is almost true, but it's not quite true. So here's the first wrinkle of the problem. So player 2, it's not, the probability of beating player 2 is not x squared. The probability of beating player 3 is x squared, but the probability of beating player 2 is not, because player 2, it's actually a little bit better than that. It's because player 2 might beat you on their first spin, but still spin again because they're not higher than their personal threshold, and then they might bust that way, and then you would still go on to face player 3 in that case. So we're going to call the threshold again T2, which is the same as the old threshold, about 5.3 something. And so, right, if the value we give to them is higher than that threshold, then again, it is going to be x to the fourth. That's going to be our probability of beating both players. But if it's less than that, now I have this problem. So we're going to consider the probability of beating player 2 for some given x, which is less than their threshold. So y1, that's their first spin. If that's less than the total we give them, then we're going to win with probability x, right? Why is that? So that's the probability that player 2 on their second spin, because if their first spin is less than the value we give them, they have to spin again. So either they're going to go over, or they're going to end up with less than x, and the probability of those two things combined is x. And it's a kind of a similar logic to why the probability of winning on the second spin in the first game was always 1 minus x for player 2. It's exactly analogous, actually. So if that's not obvious, go back to that picture and see if you can figure out why that's true. Now, if their first spin is between x and the threshold, now we get a little funky. That should be y sub 1. They win with probability of their first spin. Which the only way we win in that case is if player 2 busts, which happens with probability equal to the value of their first spin. So, but if they beat the threshold, then player 2 is going to stop. They're not going to spin again, and player 1 definitely loses. So the probability of winning for player 1 is, the probability, that's x times x, That's this kind of first bullet, right? That's the probability that their first spin is less than x, and then the second spin is one that's losing for player two, and therefore winning for player one, which has probability x, so that's just x times x. And then that second stage is that integral from x to t2 of y1 over y1, which is x squared. That x squared is the x times x, and the integral, we're going to evaluate that, right, y1 squared over 2, evaluated at t2 and x, and if you add all that up together, you get x squared plus t2 squared all over 2. Again, I'm not going to go into this calculus. You can figure out how to do that on your own, or use Wolfram Alpha or something along those lines to get there. Okay, so we have the probability of winning, which I'm going to change. I don't know that simplifying is the right term here, but I'm going to change it a little bit because I think it's cleaner to integrate later. But if our x is higher than the second player threshold, it's just x to the fourth. But if it's lower than that threshold, it's that value, that product, or I guess quotient above. So what if we spin again? So again, this is all in the service of trying to figure out what happens if when should player one spin again. Now we could do this funky integral, but I didn't do this, and I instead just relied on my intuition, and my intuition tells me that player one's threshold has to be higher than player two's threshold. Like there's just no way that it won't be, because player two is evaluating, well, I could bust, right? That's a problem. But if I don't spin again, my value is going to be lower, and so I'm probably not going to beat player three if my value is too low, so I might want to spin again. So that's a consideration for player two. Player one has that same consideration, but they have to worry about it twice, right? If they don't get a high enough number, right, their trade-off is, well, do I spin again? If I spin again, I might bust, but if I don't, there are two players that might beat me. So there's just no way that the incentive to spin again for player one is less than it is for player two. It just doesn't make any sense. So I ignored this possibility. If we wanted to be really careful, we would do the funky integral and figure out whether there were any spaces where they should spin again, or where they shouldn't spin again, rather, at low values. But it wasn't worth it to me. Even though later on we are going to have to do a very similar funky integral to figure out the actual probability of winning, but I didn't do that check here. I'm just going to rely on this intuition, and if I do that, basically it's exactly analogous to the two-player problem, except all the threes become fives, right? Basically, right? We have this. If we assume from our intuition that the T1, the threshold for the first player, is higher than T2, then I can just say, well, then the probability of winning on some given spin x is x to the fourth. I don't have to worry about all the wrinkles that we did before. And so the probability, the probability of winning for, assuming I spin again, is the integral from 0 to 1 minus x1. Again, that's the range over which I don't bust, of the sum to the fourth, which is just x1, right? It's that sum to the fifth over 5, evaluated at the high and low ends, which is 1 minus x1 to the fifth all over 5. And so if that's higher than the probability of winning from not spinning, then I should spin again. And again, I just solve this numerically, and it's about 0.65. So again, I probably, to be thorough, should check my intuition using a funky integral, but I did not, and I'm fairly confident that I don't have to. So how do you get a probability from winning here? So I basically know the probability of winning for a given first spin in the threshold. It's not quite true, right? Because I do have to do the funky integral here, because I haven't considered the probability of winning if my first spin is below the threshold. So we're gonna, and by the threshold, I mean player two's threshold, right? If my first spin is below player two's threshold, then there are some cases where my sum might also be below the threshold, and therefore, so basically I'm going to take the integral, and it gets kind of complicated, so hopefully it's somewhat easy to follow what's going on here, but basically I've got a double integral, and the middle integral is the sum of two different integrals on the very left part. So basically I want to integrate. So what happens if my first spin, so x1 again is the first spin, so what happens if my first spin is less than the threshold for player two? Well, in that case, now I have two things to worry about. The first is, well, what happens if my sum is still less than t2? So that happens if my second spin is between 0 and the difference of t2 and x1. And so in that case, my probability of winning is that value we got before, right? It's t2 squared times the sum squared plus the sum to the fourth all over 2. So that's one case. Now my second spin might be more than that, and I'm only going to go up again to 1 minus x1 because that will put me above 1, and I'll bust, so the probability is 0 there. But if I end up, but in that range, I end up above t2, so my probability of winning is just x1. It's the sum, right, to the fourth. So I'm integrating, that that fourth power polynomial over dx2, and then that whole thing that does that sum of two integrals, I'm integrating that whole thing over the first spin values between 0 and t2. So that's kind of that whole first thing, which takes up more than half the space, is the probability of winning given that the first spin is less than t2. And then the rest is more straightforward, right? The probability of winning given that my first spin is between the second player's threshold and the first player's threshold, that means I do spin again. And so I'm going to win with probability 1 minus x to the fifth all over 5. And so I'm integrating that over the range over which that's the relevant value. And then if my first spin is above my first player threshold, then it's just that value to the fourth. And if I add all those up together, again, I'm not going to go into the nitty-gritty on here. It's about 0.3052. So that is, I think that's it, but it's a lot. But I'm fairly confident that that's right. We'll see on Friday. But that's what I got. So did I make a mistake? Let me know in the comments. Otherwise, I will see you again next week. And thanks for watching. Bye.